Okay. We already kind of started going over these if you're watching the recording. So we've done the first two, but you may want to pause this if you're wanting to work through this, and then hit on pause when you're ready to go there. Any questions so far? There was one problem that my other class brought up to me where the right answer had an absolute value symbol around it. This is one of those rules that maybe you were taught it, maybe you weren't. We usually kind of ignore it when we're learning, but it's called the even. I'm calling it the even, odd rule is what I call it. So let's see. Let's say we're taking the eighth. No, let's use M or N. If we're taking the nth root of x to the n, and the result is, well, this is really m divided by n. if our index and our power is even, so we go, if this is even and this is even, and then m divided by m is odd, so the outcome is odd, then we have to put an absolute value symbol around that. Most of the time, they write in the instructions to assume that n is positive, that your values for your variables are positive. And when that's the case, we don't have to worry about this. But and so that's how they kind of get around you having to do that rule. And most of the times, we're not going to worry about that. But you can see here that a couple of my variables there, we had 2 as our index and 2 was our power. And then the resulting power after we took the root was odd, right? So we had that even, odd combination. So technically, if we're assuming, we're not saying x or y have to be positive, we should have absolute value signs around those. So this is not something I'm going to test you on, but I just want to bring that up. Some of you might remind that, or might remember that. Some of you may not. But technically, without the assumption that x and y are going to represent positive numbers, we need to put absolute values around the x and the y. If the resulting x, if it was x to the 4th instead of x squared underneath the radical, well, when we take the square root of x to the 4th, that's x squared. And so we could leave x out of that because that would give me an even result. Because x squared is always going to make whatever x we have positive anyway. So we don't have to put the absolute value. At any rate, again, I'm not going to worry about that. But if you think you had the exact right answer, but they have absolute values around their answer, that's why. Is that it's that rule there. Okay. Now on number 3, we're doing cube roots. So we want, in order to get out of jail, you got to have something to the 3rd power or 3 factors there. So we want to think of perfect cubes. Well, 1 is a perfect everything, 1, but we don't need to deal with it because 1 divided by 1 is 1 and 1 times 1 is 1. But 2 cubed gives me my first perfect cube, which is 8. 3 cubed gives you your first perfect cube, which is 7. And 4 cubed gives you your first perfect cube, which is 64. So you can see the cubes get really big really fast. So we don't have very many to check with for the number. Our first one, in fact, 8, we can see goes into 16. So we have one perfect cube there of 8. So I'm going to break that up, and remember to carry your index with you. So we have 8 times 2. And then in order for a variable to come out, it's got to have at least 3 as its power, right? The power is telling you how many of those you have. So x squared's not going to make it out. It only has 2. But y to the 4th can be broken up into y to the 3rd and 1y. So I have 2 things that can come out, the 8 and the y cubed. Your new power will be your power divided by the index. So for 8, that's 2 cubed, and that cube divided by the index 3 gives you 1. So we have 2 to the 1, or just 2. The cube root of 8 is 2. And that y to the 3rd, 3 divided by 3 is 1. But we know that the cube root of y to the 3rd is just y. And then what we have left over, we just right there, don't forget your index. We had a 2, we had an x squared, and then we had a y. Any questions on that? All right. When it comes to adding and subtracting radicals, we've got to have 2 things in place in order to combine them, to add or subtract them. It kind of follows, if you think of this as like adding variables, like 2x plus x is 3x. These are the same variables with the same powers. And when they're the same variables with the same powers, they're like terms. And the number out front tells me how many I have. So I have 2 x's, and then I'm adding another x. I'm adding 1. We don't write the 1, but this is 1x. So this can combine to give me 2 plus 1, or 3 x's. Remember that 2x is already the result of an x plus an x. So we had x plus x, which we wrote as 2x, and then we said, well, add 1 more x. So this is really 3x. That's how it should be written. We don't need to keep those separate. And the same is true for square roots that are the same number underneath, the same, we call that a radicand, which is like a $10 million word. Same number under the radical, and they have the same index, so that they have to be square roots. So basically they have to be the exact same thing, which is similar to here. We had to have the same variable raised to the same power. And we're all just x to the 1. So here I've got 6 square roots of 5. We're subtracting 1 square root of 5, and then we're adding 4 square roots of 5. And of course, 6 minus 1 is 5, and then plus 4 is 11. Is that right? No. 6 minus 1 is 5. 5 plus 4 is 9. So this is 9 square roots of 5. When we add radicals, they have to have the same radicand, the same number underneath, and the same, they both have to be square roots, cube roots, so they have to have the same index. So at number 5, we have the cube root for each one of them. Right? These are all cube roots, but they don't have the same thing underneath. But they might be able to be simplified, so we're going to look and see if we can simplify them further. The first one, and this is, that's number 5. Let me separate this out a little bit. It's not 5 cube roots of 3x. This was question number 5. So let's go to the next one. Are there any perfect squares that go into 24? Or what is the perfect cube? Sorry, I said perfect square. Is there a perfect cube that goes into 24? What's our first real perfect cube? One is a perfect everything. But the first perfect cube is 8. Does 8 go into 24? Mm-hmm. So rewriting this, I'm going to first just write it as 8 times 3. And then we have just an x. So I know I can't go any further than that. I'm just going to rewrite this. So this 8's going to come out as the cube root of 8, which is 2. And it'll get multiplied by the 2 that's already there. So now we'll have minus 4 times the square root of 3x. Now they are like terms. So we'll be able to add them together. 375, that's a pretty big one. If I look through my list here, 8 doesn't go into that. It's an odd, so we know that. 27 doesn't go, 64 doesn't go. But 125, which is 5 cubed, does. 125 times 3 gives me 375. So let's break that up. I'm going to take the 125, and that's 125 times 3. And then we have that x there. This is a cube root. So rewriting this, the cube root of 125 is 5. And then we're left with cube root of 3 and x. A lot of these you can kind of guess that maybe what's going to be left under there is going to involve a 3 and an x. And sometimes you can identify that magic number that way. But now that they're all cube roots and they all have 3x, we can add those coefficients. This was 1, 3x. So there's that kind of invisible 1. 1 minus 4 is negative 3, and negative 3 plus 5 is 2. So 2, all of a sudden I'm getting big cube roots of 3x. Say again? Where'd you get the 4? Oh, because there's 2 here already, right? And then I took the cube root of 8, which is also 2. So then I went 2 times 2. Yeah. Remember, if there's a number out there already, it's being multiplied by that number. So any numbers that come out have to be multiplied by that number. Great. Any other questions? Okay. Rationalizing the denominator. So when we talk about rational, generally that includes every number that could be expressed as a fraction that does not repeat itself with no pattern. It's easier to say what irrational number is. An irrational number is a number that repeats, is a decimal that repeats itself forever without a pattern. And we get those with square roots or cube roots or any kind of radical sometimes produces a irrational number. There's certain special numbers like pi. Because pi is 3.14, but it's actually not 3.14. It goes on and on and on without a pattern. There's a number e. Anyways, most of the time, rational is referring to numbers that are not square roots because square roots tend to produce, if it's not a perfect square, a number that is irrational. So when we say rationalize the denominator, that means turn them into rational numbers, turn them into numbers that don't involve square roots. We don't like to have square roots in the denominator fractions. There's a lot of reasons, but before the advent of calculators, which tell you an approximate value of the square root. If you had to do a division by an irrational number, the first rule is what you're dividing by, you need to turn it into a whole number in order to do long division. You may not remember that a long time ago when you did long division, but the number you're dividing by needs to be something that ends. So you need to move that decimal till it ends, then you match it up on the inside. So if you have a number that never ends and that repeats without a pattern, that's why they call it an irrational number. We can't easily divide by that. We can kind of approximate. But if we can turn it into a rational number, we can actually do some stuff there. We can at least get started. So now, if this was just square root of 5, I want to do something easier. Minus square root of 2 over, let's just say, square root of 2. The only thing I need to do to rationalize that, with fractions, we can always multiply by 1, which means multiplying the top and the bottom by the same number. If I multiply, and that doesn't change its value, right? Because times 1 is still equal to itself. And root 2 times root 2 is 2. Or it's the square root of 4, which comes out to 2. And then I just have to distribute this to both numbers on top. So this is square root of 10 minus 2. Square root of 2 times square root of 2 is 2. So now I've rationalized the denominator. I turned it into a rational number we can work with. And that makes this an easier number to actually do that division if we need to. But when I have 2 there being added, if I multiply by 2 and a root 5, it's not going to take care of the problem. For example, let's just say we try to get rid of the square root of 2 first here. That square root of 2 would still leave a square root 10. And so anyway, that's not the fastest way to do that. What we do is whatever we have there, we want to multiply it by its conjugate, which is the same numbers, but opposite, square root of 5, opposite sign. So if it's being added, we write it as a subtraction. It's called the conjugate. This is one of those special things where if we multiply a sum by its difference, we end up with a difference of 2 squares. You guys may remember this from your factoring days. And so look at what the outcome is. When I multiply it, it ends up being the difference or the subtraction of these 2 things squared. So I can square them individually, in other words. This is a quick way. If we take a sum, multiply it by its difference, we end up with this pattern. This is the pattern we notice, a difference of 2 perfect squares. So what I end up with in the denominator is root of 5 squared minus root of 2 squared. On the top, I've got to FOIL this out. They're the same. Basically, this is square root of 5 minus square root of 2 squared, but this power does not distribute to those. You have to actually FOIL it out. This is my do not do this rule, because we tend to want to just distribute that squared. But a plus b or minus b squared does not equal a squared minus b squared. The only thing that equals a squared minus b squared is a sum times its difference. Here we have to actually go. If we multiply it out, you'll see root of 5 times root of 5 is 5. So root of 5 times root of 5 is 5. But then we also have to go root of 5 times negative root of 2, which is square root of 10. And it's a positive 1 times a negative 1. So minus square root of 10. Then again, we have to go to the next. Once we've done that, we go to this one and multiply. So negative square root of 2 times square root of 5 is another minus square root of 10. And then square root of 2 times negative square root of 2 times negative square root of 2 is positive 2, because negative times negative. These two can combine, as well as these two numbers. I can go 5 plus 2. So the final thing here is 7 minus root 10 minus another root 10 is minus 2 root 10s. And then on the bottom, this became 5 minus 2. 5 squared is, or the square root of 5 squared is 5. The square root of 2 squared is 2. So over 3. Also look to see if 3 will go into both sides of the subtraction. If it'll go into both sides, you can divide it into both sides. But there has to be a common factor here and here in order to do that. Any questions about what I did there? Some of this ringing some bells of past math lives that you may have lived. Okay, I'm gonna erase this. This is why we're taking time in this section to review. This is all review from stuff from before. So don't be surprised if some of this goes, yeah, I feel like I've seen this before, but it's been a while. Yeah, this is extra review that we're doing because these are not always easy topics. This is 7. That 7's not a part of this. Okay, here we have a bunch of things being raised to the negative 2/3 power. So I threw this one, it's kind of like, all right, let's put in a bunch of stuff into one thing. First thing we notice that's different is that it's being raised to a negative power. The negative power is something that actually moves something from one part of a fraction to the other part, actually moves it down to the denominator. You can actually see this pattern. If we look at what happens here, I'm going to go 2 to the 3rd, 2 squared, 2 to the 1, 2 to the 0, 2 to the negative 1. 2 to the 3rd we know is 8. 2 squared is 4. What's 2 to the 1? 2. What about 2 to the 0? You'd think it would be 0 because anything we multiply by 0 is equal to itself, or equal to 0, sorry. But look at the pattern that we have here. From 8 to 4 to 2, what are we doing each time? Dividing by 2, right? So the next logical thing would be, if we're following that same pattern, which we are taking 1 away from that exponent, is to go 2 divided by 2, which is 1. Anything to the 0 power is actually equal to 1. And then if we continue doing that same thing, what would 2 to the negative 1 be? 1 divided by 2, which is 1/2. And if you did it again, if we divided this by 2 or multiplied by 1/2, 2 to the minus 2 is 1 over 2 squared, or 1 over 4. So negative exponents actually cause this division by whatever the n power was. Here we had, I can't really see it, but I had 2 to the minus 2. I don't know why that's the case, but this was 2 to the minus 2, and this became 1 over 2 squared, or 1/4, right? We just took 1/2 and divided it by 2, or multiplied it by a half. 1/2 times 1/2 is 1/4. So our 2 to the negative 2 became 1 over 2 squared, which is 1/4. That's just the pattern, right? That's the meaning of a negative exponent. So this negative 2/3 tells me that I'm going to move everything that's being raised to that negative power to the denominator. Think of this as being over 1. So we're just going to move everything down. So one thing I can do is make it 1 over 27x to the 6th, y to the 3rd. And then once it moves, that power becomes positive again, 2/3. All right, what does a fractional power mean? Well, it actually has the same meaning as radicals. Let's take m here. M to the 1/2 is actually the same as the square root of m. So it's intersecting with these radicals that we're working with here. I should actually write this as something slightly different. Let's generalize it a little more. A to the 1 over m. Actually, I'm going to put n there just to stay consistent. It doesn't matter, but I know your book probably does it this way. A to the 1 over m is equal to the nth root of a. Well, what if I had a number on top? Well, that number on top, it would just be a power, right? Because a squared is really a to the 2 over 1. We just don't write that over 1. So the top part actually refers to the power that a is being raised to. It's that divided by n. That's kind of the new thing, right? That's the introduction. But the number on top is that's just a power. So this really means we're going to square all of these or square root them. Another way to write this, it's just the order that you're doing it in. I can square a to the nth power and then take the nth root, or I can take the nth root of a and then raise it to the power. It's just all that's saying is what order you're going to do it in. In other words, for this problem, I can take the cube root of all these, evaluate that. So take the cube root of 27 x to the 6th, y to the 3rd, and then square that result. And I picked the cube root part first because a bunch of these are, sorry, you can't see that. I can see it. It should be the same for all of you. Let me see if I can move that. I need to do that. Here we go. Okay. I don't remember what that was. Can you see it now? Yeah. But I lost my square. Okay, it was the 1. The 1 was that. So we can take the cube root first and then square it. But I saw that all of these are perfect squares, or, there's 2 x to the 3rds and x to the 6th. You can also think of it as divided. There's 2 groups. 6 divided by 3 is 2. 2 groups of x to the 3rds. X to the 3rds are perfect cubes. And then I have 1 group of y to the 3rds. 3 divided by 3 is 1. So these are all perfect cubes. 27, cube root of 27 is, I'm going to go up, is 3, exactly. So this would be, if I take the cube root, 3 x to the second, there were 2 groups of 3x's, or you can just think 6 divided by 3. And there was 1 group of y's. So that would be, leave me with y to the 1. But notice we still have this square thing we have to take care of. So this leaves me, as I simplified, I want to square each one of these. So 1 over 3 squared, which is 9. 3 squared squared. We actually, when we raise a power to a power, this is the other rule, we can multiply those exponents. So that leaves me with x to the 4th. 2 x's raised to the second power gives us 4 x's, and then y squared. Now, this is y to the 1, so we just go 1 times 2, 2 times 2, and then 3 squared. 3 to the second power, 9. All right. Any questions on that? Okay. I want to give us some time to go over some of the homework problems. Keep in mind, and I keep on forgetting to say this, maybe I said it last time, you can work on a past due assignment after the due date and time. It's going to take 20% off for each problem that is done after the due date. But, and for ones that you already got the point for, you can work those as many times as you want. It won't change the score. So you can work after the due date and time. Some of you are going to need to, because a bunch of you didn't even start on this assignment, disappointingly to me. Not going to call you out, but I know that about half of you here haven't started on the assignment, which makes me go, did you watch the video? Did you take notes on the video? All that fun stuff. You need to have this almost complete. Maybe you're at 80 or 90% before you come here. Your goal is to get 100%. So make sure you're doing that. If you're not doing that, you're putting yourself in a bad position. If you get this done within the next 24 hours, the highest you can get is 80%. If you haven't worked any of the problems, but 80% is better than 0. So make sure you do that. Then you want to look forward to Monday, because there's another assignment coming due. So you kind of just ruined your weekend, in a sense. You're going to have 2 assignments you have to do before Monday, if you haven't done the one from today. Personally, when I try to do this in my personal life and with my work life, is I try to get everything I need to do done by Friday. What's the reward for that? I have the weekend off, right? It's not always the case. There's a lot of times where I have to end up doing stuff over the weekend, but that's always my goal. Okay. Now my other class, which meets twice a week, you guys have the benefit of kind of like this deadline here of Friday, right? The other class, they have to be on the same pace, but they only meet Monday, Wednesday. So they have to remember to do 2 assignments from Wednesday to Monday. And a lot of them, at least at the beginning, before they learn their lesson with it, are going to try to wait to the last minute. I don't know. You guys know that that's your human instinct, right? Is to put things off. Maybe it's just me. I don't know. You guys don't procrastinate. No, it's done like way ahead of time. Just know that that's your human trait. So unless you like put something in the way of that, that's going to be what you're going to tend to want to do, which is always a self-defeating thing, right? Get yourself started on the right foot. If you're a little behind, let's change that course for the weekends. It's a small price to pay to be on the right track at this point. Okay. I'm going to change our share. allow multiple. Okay, place screen share. I'm guessing it's going to make me log in again. All right, questions you'd like me to go over. They're basically going to be similar to the ones we've been working with. But any ones that you have some questions on, we can go over together. And you guys who are online, you can feel free to jump in on the chat box. I'm monitoring that as well. It only takes the first person. I know that sometimes the mental games we play with ourselves is we think, I'm the only one who had trouble with this problem, so I'm just going to wait and figure it out on my own, or I'm going to talk to the teacher after class. Just assume that if you were doing your work and you had, this is what I did. Assume that if you had problems with a problem, there's probably half a dozen to a dozen people in the same class that had the same problem as well. But so with that, know that you're not the only one who probably had a problem with that problem. People tend to have similar problems that they struggle with. So you're helping those other people who won't speak up by speaking up. Plus, also, you're paying for the class, right? Get your money's worth. Let's do number 10. Okay, yeah. So a couple things to remember, because there's a lot of rules that we throw out. These are, review, but it's a lot to review. Make sure you write these down so you can reference them on a piece of paper. The general idea with multiplication and division, for example, and this applies for any radicals, square root, cube root, what have you. The nth root of a times the nth root of b is equal to the nth root of a times b. When we're multiplying or dividing, square root of a divided by square root of b is equal to the square root of a divided by b. With multiplying and dividing, the rules are a little looser. We don't have to have the same number under the radical in order to multiply. In fact, this is how we simplify. We took a number that was one number, we broke it up into the square root of two different numbers. That's how we pulled out perfect squares and perfect cubes out of our radical, is working that kind of backwards. The same is true for division. Multiplication and division kind of follow that same rule. But with addition and subtraction, if I have the square root of a plus the square root of b, this does not equal the square root of a plus b, right? That we can't do that. In order to add or subtract, we have to have the same index and the same radicand. So there has to be another a under there. And when we add them, we add the coefficient. So this is a 1 and a 1. We combine them by adding what's out there. If we were I should not put subtraction there because a minus a would just be 0. So we treat with addition and subtraction, that's a little harder to get them together. They have to not only have, they not only have to both be square roots or cube roots, they both have the same number underneath. So if we're trying to subtract the cube root of 81 minus the cube root of 375, we can't do it because 81 and 375 are not the same. But what we can do is look for and simplify them individually first and see if there's any perfect cubes that go into these numbers. Remember, my cubes are much more limited than my squares. We have 2 cubes, so we have to start at 8. 8 doesn't go into either of those. 3 cubed is 27. 27 actually does go into one of those 2. Which one does 27 go into? That's 64, 5 cubed. By the time you get to 5, it's usually bigger than your number. But 27 goes into 81 3 times. So in other words, this can be written as a cube root of 3 times the cube root of 27. I should have written them in a different order, but the cube root of 27 becomes 3, and then we still have a cube root of 3. But 27 is going to 375. We saw 375 earlier. Yeah. Cube root of 27. If you wanted to write 7 in terms of its root, it's not 27 cubed. 27 cubed doesn't give you 81. Right, 27 cubed would give you a really big number. It's 3 cubed. So the cube root of 27 you can write as 3 cubed. Right? Cube root of 27, if you were to write that in terms of its cubes, is 3 cubed. Does that make sense? Yeah. I see where you're getting at, though. I see exactly where you're at with that. 125 goes into 375 3 times. So I can break this one up into 3 times 125. Sometimes this does weird things. Times 125. And so the 125 comes out. 125 is 5 cubed. So the cube root of 5 cubed leaves me with 5. And then we still have the cube root of 3 under there, which is good for us. It's allowing us to actually combine these together now because it's the same index. They're both cube roots, and they both have the same radicand, which is 3. So we can subtract their exponents. 3 minus 5 leaves me with negative 2 cube roots of 3. Here, you got to use these little boxes down here. So we're doing a cube root of 3. Oh, and then we had negative 2 out front. So minus 2. Which, when you use the word simplify, is this simpler? Yeah, that's way simpler than what we had written before. Does that answer the question? Yeah, these just take practice. You need to review these. Make sure you practice. If you find a couple that you're like, ugh, I don't want to work at another one of these problems, somehow you get to the right answer, but you don't like it because it makes you have to think hard. That's a sign that you probably want to regenerate a couple more, just get some more practice with it, right? This is all practice. And it pays off down the road. Because then when you're doing another concept that's new, that involves your knowledge of this, you got this part down. You just need to build on that. Yeah.
When it says simplify, that's just it saying like, just try and find the easiest expression.
Yeah, simplify is a very general term, right? Like, well, what does that mean?
Yeah.
None of this is simple. It means to get it down, with the radicals, get anything out of the radicals that you can get out. And then if you can add these together, so you don't have two terms, we have one term, right? You kind of think in those terms, like, is there anything I forgot to do? Is kind of this idea of simplify. So get as much as you can out of that and add and subtract as much as you can. Yeah, because like this is simpler than the previous. But then you're like, oh, I can do one more thing. So you kind of always think, is there one more step I can go? Anybody else? Questions that you want me to go over? We got a couple more, like 2 more minutes. Okay. If you haven't started working on this, you need to jump on that horse, get this done as much as you can. Remember, it comes due about an hour after class, 10:30. But today is not the day to work on it. There's not enough time for you to get it all done within that hour, even after watching my amazing presentation to you. You still have to struggle through all of these. Homework is the struggle part of the learning. And so don't be surprised when it's not easy all the time. Doesn't mean that you don't get math. Doesn't mean you can't do math. You just have to push through those doors of struggle. And once you do that, then you get better at it. All right. Have a great weekend. I'll see all of you on Monday. Uh-huh. Mm-hmm.
How exactly are you supposed to figure out when's the next nearest due date?
Go to the main homepage. Yeah. Look at the calendar.
Oh,
You can see what's coming due. Oh, and they give you check marks on there.
that's why I missed it. I thought it was due because of, I thought it was this one and this one and this one.
Yeah, I wouldn't go by that. That's, there's a lot of things I wish they would do better. That's one of them. So like rearrange the order that it's in. One thing you can do as well, on the page where it has the PowerPoints and the videos, those are always, I can move those. And so I put those in the order that we're going.
All right, and one last question. What am I supposed to do about the video quiz, or is that just done?
So the video quiz is due at the beginning of class. Which one is that?
It's the one for the radicals, the one.
Oh.
I thought it would be up here. That's why I thought it was.
Yeah. No, it's okay. I'll extend that out for you. Just hold on one second. It takes me a minute to go through, and I want to get through. Yes.
My question was, on Monday, there's an assignment for 1.3 and then a quiz for 1.4.
Oh, is there?
Yeah, and that's for like throughout the week, I think.
Okay.
Is that
Yeah.
how it's supposed to be?
No, because I switched. I put A4 as our Friday's assignment, and 1.3 used to be on Friday's date.
Yeah.
So I moved that, but I obviously forgot to move the quizzes to line up. So I'll switch that around. Yeah.
So like when I'm watching like the lecture videos and the presentation,
Yeah.
it's like I have like difficulty like understanding like what's like a good way to like take away the information and like remember it.
Well, take notes, right?
Because like, I'm taking notes. Like, most of the time.
Start working on them. Sorry, I gotta get out of here for next class.